Hi, well, thanks for inviting me to talk about our work on the nature of light. I'm honored to be considered. Um, Most of my career, I've been doing biology research on diabetes when I was a NIH principal investigator down in San Diego. And then about 20 years ago, I left that, started teaching at Palomar College. And ever since I was in high school, I knew there was a problem with the idea of time dilation due to motion based on a thought experiment using a light ray. And so I always wanted to get into addressing that problem. And so what I'd like to do is summarize the key points that we've discovered that have been published in several articles that we've had over the years. And actually I could list those, because if I share my screen, I could show you a list of those, because you might want to check them out, because anything I might miss in the discussion here, you can find all the details on it in these articles. The first one was published in 2013. That's after having spent a lot of my spare time working on the problem. And the latest was published this year. So the gist of it is, what we wanted to do was to figure out what happens to what's known as the nature of light under conditions of secular aberration, where a lateral moving source produces light of a different quality than if the source were stationary. Because we need that kind of information in order to be able to interpret these time dilation theoretic diagrams to figure out what's really going on. Does time really dilate due to motion, or does it not? And so what I found what I had to do over a year of experimentally trying to get to the bottom of it. I found that anytime the Earth rotates on its axis throughout a 24-hour day, a lot of the land where I would put this laser light device was unstable. And I was getting erratic results for looking at the spot that the laser light produced 30 meters away on a target continuously for a 24-hour period, until I finally realized that the library at our school is built on a granite mountain, and it's extremely stable. And so I also built, one of my students, his dad has worked for the Navy, and he was a metalsmith, and he was able to build this very strong angle iron metal device with holes drilled in it to hold this laser in position, so it could not rotate in any direction or laterally moves right or left, up or down, forward or backward. And this was mounted on a concrete retaining wall. And the light was turned on for 24-hour periods at a time with a target 30 meters away to trace the reflected spot that was produced by the laser. In the daytime, you had to hold a cup over the light beam so you could see it, because the daylight would wash out the color and you couldn't see it well unless you did this. Nighttime, it was no problem. Because the gist of it is, I wanted to figure out, because the Earth travels 65,000 miles an hour in its orbit around the sun, I wanted to figure out that if you shined a laser beam 30 meters northward like this, in vertical direction, as the Earth was twirling like a figure skater going around the sun, spinning around every 24 hours, what would happen to that spot? Would it shift on the target, or would it stay on the same exact position? And the reason I chose 30 meters is because in the time it takes light to travel 30 meters upward, the Earth would travel about 3 millimeters along its orbit path around the sun. So if the light photons leaving the lateral moving source this way were, after being detached from the source and produced in the atmosphere, and the Earth and the source were moving 3 millimeters distant while the light was traveling forward, would the photons travel on a course that's independent of the source that has detached from it, or would it pick up the lateral velocity of the source and land on the target spot anyway. That was the ultimate question. Like I say, it took quite a while to get the conditions right, but we finally got it all done. And in the daylight hours, when the Earth is rotating counterclockwise and yet heading counterclockwise around the sun this way, the east coast is trailing rather the west coast. And so if the photons were separated from the target and did their own thing, they would land to the right of the target, 3 millimeters shifted from where they would have landed if the Earth wasn't moving. But then when the Earth spins around like a twirling figure skater, so at nighttime, it's still traveling counterclockwise around the sun. But now the situation is reversed. Flashlight's back here and out of in the shadow of the sun now. Well, now the east coast is leading the west coast. And the photons, if they were disengaged from the source and traveled in their own direction, then they would splatter on the target 3 millimeters left to the center. So it was like a nighttime was the control for the daytime and vice versa. And it turns out that the spot never shifted over 24-hour paths over and over and over again. Didn't matter what the season was or anything. So I knew that the photons themselves are actually departing the source, picking up the lateral velocity of the source and moving to catch the target in its new shifted position later, after it traveled 30 meters north. In the nighttime, it would move this way and join the target. In the daytime, it would move this way to join the target. So that was the crucial result that we needed to be able to go further. So it's not case one, it is case two, where photons leave a lateral moving target sequentially and make a beam of light, but the direction that they travel is an angled direction towards the target to hit the center spot of the target at all times, whether the Earth is traveling towards the east or towards the west. It wasn't this case, where the photons did their own thing and the target could shift right and left, having the photons splatter on different positions from the center. So again, if you had a source and a target that were shifting to the right, this is mythical, but if you could shift it so fast that it would be, fast enough to make a significant percentage of the speed that light was traveling forward in the first place, well, the first photon would leave when the source is over here, and it would angle travel to the target in this manner, and eventually it'll land on the target when the target reaches its new shifted position over here. But meanwhile, a second photon could be described as having departed from this new shifted position. It'll also pick up the lateral velocity and travel at an angled direction this way. So it looks as though it's following the other photon, but they're all angle traveling towards the target. And then by the time this first photon splatters on the detector, the source is now in this new position where another photon is being formed. So if you look at a light ray, this was done in a steam cloud system, a light ray coming from this laser that you can see because the photons some of them are being reflected by the steam. And it looks like a straight line that the photons give the illusion that they travel straight from here over to here. But because the Earth is moving laterally, in reality, each individual photon, yes, they're trailing each other, but they all have angled travel to get there, leaving when the source is at different positions. So you can diagram it like this. If you were looking at some object that had light reflected from it and was heading toward your eye, yes, you would see the image of the object when that light arrived at your eye down here, but that image came from a location that was shifted to where the object, the source of the light, used to be, but now isn't when the light arrives at your eyes. So every time you look at an image of something on Earth, since the Earth is always moving and orbiting, depending on the direction you're looking and this and that, the point is, whatever the lateral velocity of the Earth is for any object that you're staring at, you're always looking at an image of the object that was located at a different position than what it is now by the time you see that image. But yet, because the photons follow this path, angle traveling, making the images line up in a straight line like this anyway. The image that you see is directly in front of the actual object's position at the time the light arrives. So that's pretty cool. Everything you look at, you're looking at an image that was produced before at a different position, but it's now still in front of the actual object. So you can reach out and touch it. You won't miss it, but because you're actually touching where it now is, even though the light came from where it used to be. So it makes light even more elegant and miraculous than what I always thought it was. Now this is a typical diagram in most physics textbooks around the world, trying to demonstrate that time slows down for a moving observer. But notice the event really is one event that's being described by two different observers. And whatever the time is that actually takes place is a single time because it's one event. But a stationary observer would see this light flash down here when the ship was over here. Later on when the ship is over here, the light, the photon anyway, reaches the target at the top. Well, he would think that the time it took to do that would be this distance divided by the speed of light c. And that's a reasonable interpretation. But a person in the ship, in this diagram, would only sense, if he didn't correct for the fact that he was moving laterally and he didn't know it, he would think that the time for this event was only the height of the ship divided by c, which is a completely different computation than down here. So the mistake was that the two different times actually had meaning, and it was blamed on the fact that this observer was in motion. So the idea was that it came into the literature that time actually slows down. Time itself actually slows down simply because someone moves. But of course that's mistaken. This time is just an erroneous time that was not the time for the actual light event that took place. And notice light doesn't go through a wall of a ship, and this couldn't represent a ray because when this photon had left it from over here, well, the new photons leaving are from the source where it now is over here. So this diagram has many issues. So a better one would be this, where the photon leaves the moving ship here, stays inside the ship, of course, and later on the ship's over here, and then the photon arrives at the target. And the real time is big L divided by the speed of light. The person inside might mistakenly think the light only went up, just like we looked at the beam in the seam cloud that I had. The photons didn't only travel straight from the source where it now is over the target where it now is. It traveled from where the source used to be to where the target now is, which is a longer distance, just like here where this observer actually sees it. So the mistake for a person riding inside the ship would be he would think it was only this height over c, knowing the speed of light is fixed at c. At least the intrinsic speed is. But notice, even a person standing still over here in front of the ship would also mistakenly, mirage-like, think it only went this distance up as well. So the mistake has nothing to do with motion necessarily. It's just an error, computation error. Since this angle here is d divided by L, the sine of that angle is d over L. If you put that into the formula for the time, which is distance over the velocity, it turns out you get the same expression. 2d over c sine theta is the same thing as 2L over c for the entire round trip. So there is no difference if the observer who was moving with the ship had used c sine theta for the component of velocity in the northerly upward direction, he also would have gotten the same time that the stationary observer had gotten. So the mistake made has really hurt a lot of the literature in theoretical physics, when people assume that motion causes time to slow down, when it really doesn't. Another error is that people might think that since the velocity of light is so fast that it can't be exceeded. And that's another thing that needs to be clarified, because the intrinsic velocity that light has is indeed speed c from the location in space at which it leaves its source. But that does not mean it can't be exceeded. Its intrinsic speed is constant, but if you had two beams, one pointing south and one pointing north, I took these photographs, and 1/30th of a second when this light ray was photographed, the reflected ray was photographed, the photon must have traveled from San Diego all the way down to hundreds of miles below the Mexico border. When I took this one, 1/30th of a second, 32nd of a second, the light would have traveled from this spot 300 miles north of Santa Barbara. But when you light two beams together at the same time, well, what you're doing is you're now illuminating space at twice the speed that a single beam could have done it. So the space is being illuminated at a velocity of 2c. And on top of that, just because the intrinsic propagation speed is c doesn't mean that velocity components are c. Just like in the above example where the velocity upward towards the top of the ship was c sine theta, well, same thing here. If you light a candle and look at all the beams that come out in all directions in 3D space, you could say that the velocity in the horizontal eastward direction is indeed c for the photons that travel in that direction. And the velocity north is c, the velocity south is c, velocity west is c. But this northerly heading photon has a horizontal velocity component of 0, just like this one has a northerly velocity component of 0. So velocity is also not always equal to just plain c. C is the speed that the light has in the direction of propagation only. And another thing about it is that, relative velocity is different than intrinsic velocity, and relative speed is different than intrinsic speed. And the intrinsic speed that the light has is indeed c in any direction from the location in space where the photons leave the source. But because this candle is lit on a moving Earth, as soon as the photons are produced, one is traveling at intrinsic speed c from the spot it was when it was formed. But while it's traveling, the candle system itself is attached to the Earth and is moving. So the relative velocity between the wavefront and the source now is not c. It's less than c, and if it's traveling in the direction that the light front is traveling. It's greater than c if the photon is traveling opposite direction of what the source is now traveling, being on Earth. So you have to be careful when using velocity components and relative velocity in a light experiment, especially when you're trying to calculate the time. Another aspect of light that we needed to know is, what is the proof or the solid, really good evidence that light has no mass? Because when courses teach what light is, it's massless electromagnetic radiation, where each photon is a minuscule little packet of EM energy that propagates through space at intrinsic speed c. And later on, after this relativity idea came into play, the idea was that, well, maybe light really does have a small mass. So we had to get to the bottom of that. And the best way to do that was just to shine a laser light through a glass of water like this and analyze what it's doing. Well, in air, it travels at about 3 times 10 to the 8th meters per second. But in glass, it travels about 2 times 10 to the 8th meters per second. And then in water, 2.3, glass again at 2, and then air again as it leaves the glass at 3 again. So while it's in water, it's traveling at this constant speed for water all the time it's in the water. And when it's in glass, it's traveling at this speed all the time that it's in the glass. Well, particles with actual mass and possibility of friction have no such ability to do this. Moreover, when the light leaves the glass, enters the air, the speed is immediately the speed that light must be to travel in air, which is back to 3 times 10 to the 8th meter per second again. It's an acceleration that objects with mass simply cannot do. And we can thank James Clerk Maxwell for deriving originally the specific formulas for the speed of light. It's equal to the electric field magnitude over the magnetic field magnitude, or 1 over the square root of the permittivity of space and the permeability of free space multiplied together. It's also equal to the frequency times the wavelength. It's also equal to the distance that the light really travels divided by the time. And so all of these formulas give you correct answers for time, for example, when you use them properly. And notice there is no term for mass. There is no mass in any of these equations for light's intrinsic speed. So there is no doubt that light is massless EM radiation. Electric fields have no mass, magnetic fields have no mass, and EM radiation also has no mass. The difference between light, EM radiation, versus an individual separated electric field or a magnetic field is light is energy, given by E equals h times frequency, where h is Planck's constant. Electric fields and magnetic fields don't have any energy. They exist around charges or around magnetic dipoles, and they don't really have energy unless another dipole is in a magnetic field or unless another charge is in that electric field. Then there can be an energy. Light itself is an internal system of energy that's transported indefinitely through space if it's uninterrupted by matter. So when I was in Washington, D.C., I wanted to find the statue of Albert Einstein, who first developed the theory behind lasers, which was really excellent. He also discovered the photoelectric effect, got the Nobel Prize for that. But he also made this conceptual error about time dilation. So I noticed that when I was there, I looked at what was sculptured at his statue, which is a quote of his that says, "The right to search for truth implies also a duty. One must not conceal any part of what one has recognized to be true." So I think if he were still here, he passed away when I was around 15, he would want this idea of time dilation to be corrected. It's funny because all the statues in Washington, D.C. cannot be over, I believe it's 11 feet tall or 9 feet tall, something like that. But his statue, his whole height here was 11 feet. But the reason it was allowed is because he's sitting down, so he still didn't exceed the vertical height requirement. I thought that was kind of interesting. Other work I've been trying to get involved in a little bit is, what are the as a chemist, I wanted to know what are the chemical explanations as to why when light interacts with mass, it can sometimes be transmitted through the material. If it's something like, pure diamond or glass, it's transmitted through a translucent substance, or it's fully absorbed in a black body like graphite, or it's pretty much fully reflected in something like aluminum metal. What is going on? And that's proved to be kind of difficult. It's not only due to the atomic arrangements in the lattices of these materials, but also I think it comes down to the electronic structure and arrangements in the system that's at hand. I mean, graphite is pure carbon, but absorbs all the light. Diamond is also pure carbon, and the crystal lattice structure is different from the two. Graphite here, diamond here. Light goes completely through this, and it doesn't go anywhere in this except to be absorbed. Here, metals have what are thought to be a sea of electrons roaming all around in them, so they're very conductive of electricity. But yet light is completely reflected off of them. Now, when light is absorbed, it must be that the electrons in there are able to be jostled around by the light. In theory, any substance, because light has no mass, light could go right through it, except it's found by experiment that some things allow light to go through well and other things don't allow light to go through well at all. In fact, some absorb the light well for various chemical reasons. But it's also true that even metals can be translucent. It's been discovered you could take a thin layer coating of gold, pure gold on a substrate, and light goes right through the gold. I think it's kind of cool that in the biblical revelation it says in heaven there's going to be gold structures that are as translucent as glass. So it's not unbelievable how this system though here with carbon in an arranged lattice structure like this allows all light to virtually all go through, but treating the diamond with X-rays and changing the structure, even though it's still pure carbon, arranged differently, the light is completely absorbed. It's quite amazing because the electronic configuration is 2s2p2 for the ground state for the carbon atoms in all these systems. And so it's quite amazing. And this is outside. If the sun is hitting concrete, the light is reflected. But asphalt, the light is absorbed. But asphalt has a lot of aromatic covalent molecules in there, and it's understandable why light would be absorbed by systems where the electrons can be energized easily. This calcium silicate salt that makes concrete is an ionic compound where you would not necessarily think would reflect the light, but it does. You know, it has the same ingredient that glass has mixed in with the calcium silicate. Table salt, when it's an ionic crystal, is transparent, and yet grind it all up, crunch it all up, it's now reflective. And even though the sodium chloride molecules are exactly the same, they're just arranged in a different position in a lattice. So it does have a lot to do with molecular arrangements in 3D space. Like I say, it also has to do with electronic structure as well. The relative transparency of a material. From the sun, they can either spin to the right or spin to the left like little spinning torpedoes. These massless, little minuscule packets of electromagnetic energy will trace out a sinusoidal pattern of the electric field amplitude and its corresponding orthogonal magnetic field amplitude. And they self-induce and self-annihilate each other in succession as light travels forward in perpetuity if uninterrupted by matter. And the energy of the light, of course, is related to the frequency or the wavelength of the light. And it turns out the amplitude is also related to the energy because it's really equal to the maximum value that the electric field would have, which is proportional to the square root of the energy that the photon has, where the total energy has to be divided by 2 to get just the energy of the electric field part, because the magnetic energy is equal to the electric field energy as the light propagates forward. So I want to look at, what happens to the penetrability of light in a substance like water as a function of, energy of the photons. The thing is, red light is absorbed well by water simply because that is the frequency that matches the rotational motion and the vibrational motion of bonds in the water molecule, the flexing motion of the bonds. And so that is one reason why certain colors of wavelengths of light can be absorbed. Independent of what I was looking at, I was wanting to see what happens to the absorbance as a function of energy of the light. So that complicated the issue. But on the other end of the spectrum, UV light is absorbed by water as well, pretty well, because of I'm thinking that the pi bond systems that are in water when oxygen gas, carbon dioxide gas, and nitrogen gas with its triple bond are all dissolved in the water. And that would do a lot of absorbing of UV light, these pi cloud transitions. But if you look at the middle colors, outside of the infrared and the ultraviolet, between red, green, and blue, you see that the 50% absorption values occur for blue light at 20 meters depth, green at about 10 meters depth, and red at a couple meters depth. So the higher energy light does seem to be penetrating into the water better than the low energy light. These are not my experiments. These were data that have been published by others. But the correlation seems to be there. The more energy that the photon has, maybe the deeper it can penetrate, at least into water. So I did a graph of that, of the joules of energy per photon as a function of depth of 50% penetration for the red, green, and blue light. Blue light goes deeper, has a higher energy per photon. This just helps kind of understand what happens when a photon enters from air, where it's traveling at a certain speed with a certain frequency and wavelength, and enters into glass, where it now has a shorter wavelength. But because it has a shorter wavelength, and yet the frequency of the light is still the same, because the frequency is determined by the source that produces it. Well, the speed of light in the glass is therefore slower. And then, of course, the light speeds up, regains its original wavelength, speeds back up again when it enters the air. Here I figured out a formula for the the amplitude of the electric field, the highest point the electric field goes when a photon traces out a sine curve like this. That should be the square root of 2 times the energy of the wave divided by the permittivity of space times the sine of energy over Planck's constant times time. So as a function of time, this would graph the magnitude E that is traced out by a photon traveling in a given medium, given energy. So one of the important reasons, really, of course, to study light is because we want to get to a point where we don't have to rely on so much nuclear power with all its plutonium waste and the radioactive gases that can't be trapped that are emitted from these nuclear power plants and so on. It's just a real problem storing these wastes that have 100,000-year half-lives and things like that, and they're very toxic. We want to be able to get to where we rely more on solar power, I think, where we rely on nuclear fusion that occurs on the sun. And another reason for studying light, of course, is it's because it's so important for preserving life, because light really is responsible for producing in photosynthesis all of the world's main primary food supply, making sugar in a plant, where the light catalyzes or causes like a photoelectric effect in a chloroplast, where it ejects an electron, and which ends up going down a protein chain. I call it a protein wire, and lands on nicotine adenine dinucleotide phosphate ion to reduce it to NADPH, which then supplies the hydrogens and electrons to be forced onto carbon dioxide to make sugar. And in the meantime, the electrons that are leaving the chloroplast are replenished by electrons from water from the roots of the plant, which releases oxygen gas. So photosynthesis caused by light is not only responsible for the world's food supply, but also is responsible for regenerating oxygen gas in the atmosphere that we can breathe, and for removing carbon dioxide waste gas from the air as well. So I view photosynthesis as kind of an electric circuit where light hits the chlorophyll molecules, ejecting electrons, which then travel down a protein wire, landing on NADP to make the reduced form to later be used in the production of sugar. This also produces energy, ATP, for the plant. I used to work for Dr. Andrew Benson down at Scripps Oceanography. He was my mentor for many years. He passed away a few years ago. He discovered the light-independent reaction in photosynthesis where carbon dioxide is trapped by ribulose phosphate to make eventually sugar. So similar to a photoelectric cell, I mean, a plant is really kind of an electric circuit in the sense that the chlorophyll has this structure with roaming resonating electrons that can be energized easily when the right frequency of light hits it. The light knocks the electrons off the chlorophyll. Again, like I said, they travel down sort of a protein wire to land on NADP to make NADPH. And what I call the anode is the water releasing electrons and oxygen gas into the chloroplast. And then the cathode would be where the NADP plus accepts the electrons at the end of the protein wire to make NADPH. So it's kind of a little electric circuit that goes on every time the sun rises, and all the green things that you see are undergoing this completed electric circuit. And so what I did is I did some experiments applying a voltage across a succulent plant because I wanted to determine where the electricity actually flows through a plant when you do this. Because it's similar to a wire, but not exactly like a wire. A metal wire would have electrons flowing all around the entire surface of the wire, no matter what size it was, to go from the anode to the cathode. In the plant, being a salt, basically a salt solution of cytoplasm in there, the electricity flows from the anode to the cathode in a restricted domain here. You notice it eventually was significant enough to burn the tissue. So this I wrote up and sent it to a company that uses devices that generate electric currents to treat tumors in people. They actually anesthetize people and surgically put electrodes across a tumor tissue and electrocute it to death. So I wanted this data, to send to them. So that's really what I wanted to share. But again, if you want all the details and all these things that we've been studying, please consult these references. I think they're pretty good. Did the best I could. Thanks very much for allowing me to share this.